Okay, so yeah, I titled my work an exploration of real-time computer graphics. So kind of the high-level goals of the project were to explore computer graphics techniques and the various kind of theoretical foundations behind them, and then apply them in building a real-time rendering engine utilizing Vulkan and C++. And the main focus is on physically based rendering techniques, which are rendering techniques that we'll explore further, but basically the goal is to create as realistic of a rendering as possible while still keeping the real-time interactivity of the system. So it all starts with the graphics pipeline, which is kind of the key foundational concept to computer graphics. It's a series of steps that are carried out to transform the input vertices and textures and everything into the final rendered image that you see on the screen. And so this is just kind of a general high-level abstraction that is used throughout computer graphics, so much so that it's referred to as just the pipeline. And so it's composed of a series of fixed functions, which are standard hardware-defined functions that are done the same for all applications, and user programmable shaders. And so the pipeline starts with inputting vertices, which are the 3D points of the meshes that you're rendering, textures, which provide color, data, and various other forms of information, which we will discuss later, and various transformation matrices. And so we begin with the vertex shader, which is in charge of taking these points and transforming them throughout the scene. And so looking at this example, the triangle has just been rotated and scaled up a bit. And then it's passed into the first fixed function stage, which is shape assembly. So this is where the graphics card interpretates the various vertices and makes shapes from them. So typically triangles are used just because they are easy to draw, and it happens to be that all 3 points lie on the same plane. And so you can compose any sort of 3D model from a whole bunch of triangles, put together. And so after it's been triangulated, you go to the rasterization phase, which is where you take these points and turn them into pixels to be displayed on the screen. And with the rasterization completed, you move into the fragment shader, and this is where it gets really exciting. The fragment shader is where you calculate all the lighting properties and you color the fragments. And so this is really the kind of the big bulk of computer graphics is in the fragment shader, and this is where you spend most of the time, and it's the most computationally complex part of the pipeline. And then finally, you do some blending, which determines how you kind of blend the colors together and output it to the screen. So in computer graphics, there are 3 main types of 3D spaces that are utilized. You have model space, which is the 3D space that the object is defined within. And so this is, irrespective to any other objects within the scene. It's just the pure vertices that the model was created with. Now, world space is where you add kind of more context to the broader scene. This is where you define the positional and rotational relations of the objects with respect to other objects within the scene. And finally, view space is taking that and shifting it to the perspective of the camera. Even though there isn't a physical camera, we often refer to it as a virtual camera because they share similar properties. Now, within computer graphics, rather than physically updating these vertices in memory, it is faster to compute the transformations each frame. And so GPUs, the graphics processing units, are especially designed for carrying out these kinds of matrix operations and do so very fast. And so these vertex transformations are done utilizing these special transformation matrices. You have your basic operations of translation, where you shift the origin of the model, rotation, where you rotate about an axis, and scaling, where you enlarge or shrink the mesh. And so, as I mentioned earlier, this is done each frame by taking each of the input vertices and multiplying it by a transformation matrix. And because of the properties of matrices, you're able to multiply together multiple transformation matrices to create a composite transformation matrix that carries out all of the translations that you want to. Now, in general, there's kind of a order of operations for carrying out these transformations. And so the first thing you want to do is scale. And the reason for this is This is done in object space, and so you're scaling it about the origin of the object. Next, you want to rotate, so you get rotation about the origin of the origin axes of the object, and then finally you translate it after those two. If you translate it first and then rotate it, you're no longer rotating about the origin of the object, and so you don't get the desired effect. And so finally, computer graphics uses these four-dimensional homogeneous coordinates, where we introduce a fourth W component. Now, for this to be correct within the context of computer graphics, the fourth component must always be 1. And so this allows us to introduce an interesting behavior to kind of gain depth perception and perspective by shifting that W component and then correcting it back to 1. We change the overall scale of the axes of the scene, and it gives us various types of projections. So the analogy that I find best describes it is the effect of moving a projector closer to a screen. As you move it closer, everything gets larger. As you move it further away, everything gets smaller. So by shifting the perspective of individual vertices, we're able to shift the entire scene, giving it various projections that better align with how humans perceive the world. And so this is a key process, and technically the fourth 3D space within computer graphics, which is the perspective projection. So generally there are two main types of projections. So we can think of it as we're projecting the 3D scene onto the flat 2D screen that is the monitor or the final image. And so orthographic projection is where all of the projected points are parallel to each other. And so this gives you kind of a flat, depthless image, but it's useful in many engineering applications because it preserves proper angles and doesn't distort the angles of the objects. Now, perspective projection has all of the projected lines of projection converging to a single point, and this gives you a more human, for lack of a better term, view of the scene. It gives you kind of a better depth perspective, a wider field of view, which is the total area of the scene that you can see. And all of this is done by special projection matrices that change the W value for the various vertices. And then before the final scene is rendered, you convert it back to a 3D point by making sure W is 1 and then just removing the W component. And so to ensure W is 1, you just divide the entire vector or point by whatever W is. Now, shading models are, in my opinion, the most exciting part of computer graphics. I mean, transformations and stuff is pretty standard. It's the same across the board. Shading models are where we calculate, the propagation and effects of light within the scene. And so this is where we are adding color and shadowing and all of the, visually interesting aspects of the scene. Now, typically there is a trade-off between realism and performance. In the movies, for example, we're not interested in targeting a real-time interactive timeline, and so they're able to spend several days rendering their scenes to get picture perfect rendering. But you can't go in and be like, let's just shift the camera all of a sudden, because it would take another day to render. And so typically within real-time computer graphics and applications such as video games, the visuals aren't as realistic as a movie, but the trade-off is we're able to interact with it because the scene is rendered in real time. Now, for reference, the target is 60 frames per second, which means that the entire shading computation, everything has to be done in roughly 16 milliseconds, which is faster than the blink of an eye. And so it's a lot of work to do in a very little amount of time. Now, physically based shading isn't really a specific shading method. Rather, it's kind of a set of guidelines and rules that we try to apply to our shading models to make them more based in physical observations of materials. And so really the core principle is to not violate any physical properties of light. And the main one is conservation of energy. Basic idea is that you can't have any more energy outgoing than is ingoing, unless it's an emissive material, but that's a whole different thing that we won't cover today. So physically based shading models are great because they give you a greater level of realism because the parameters that you are utilizing in your shading model are based off of physical observations of materials. And additionally, they follow this principle of everything is shiny. Because if you think about it, almost all materials in the world give some sort of reflection. Even a super matte material still has a slight reflection to it. And so a lot of these models are based around how do we model and simulate reflection, mainly specular reflection, which are these bright highlight spots that you see on various materials. So it all begins with these things called bidirectional reflectance distribution functions, or BRDFs. BRDFs are used to model the amount of light that is reflected from a surface, mainly in the specular reflections, depending on the location of the light source and the viewer. And so these are typically used for attenuation of the specular reflection, which is really a fancy way of saying determining how bright it should be. And so a common way of modeling these is to plot them with a constant light vector, which is this green line here, and then plot all of the BRDF values for the possible viewing angles of the upper hemisphere. Now, the reason why we use the upper hemisphere is because the lower hemisphere is below the surface, and for the sake of computer graphics, we consider below the surface to be just impossible. If you're behind the surface and the light source is in front, you're not going to see the light for the most part. And so we cut off any values that are below the surface. And so looking at this one, for example, you can see that when the viewer is aligned to the reflection vector of the light source, they see a super bright reflection due to the extremely large value of the BRDF. But for any other viewing angle, the reflection is much smaller. And so BRDFs allow you to model various 3D properties of materials, and it gives you a bit more realism by swapping out the BRDF that is used depending on the material type. And additionally, it allows for a bit of artistic control in stylized applications where they're not going for realism, but they want to add a certain artistic flair to it. They can utilize different shaped BRDFs to change the properties of light reflection for the materials. Now, another key part of physically based techniques is this idea of microfacets. So in real world, there's no such thing as a perfectly smooth surface. Everything is composed of these tiny little microscopic imperfections. However, if we were to physically model these with geometry in computer graphics, it would require a ridiculous number of vertices, which is infeasible for a real-time application. And so rather, we model this utilizing a statistical model to try and add in the effect of this microgeometry on the lighting in the scene. So we have two kind of normals that we are concerned with. We have the macro surface normal, which is denoted as n, which is the actual surface normal of the geometry. And in addition, we have the micro surface normal, which there are multiple of, and we denote it as m. But the basic idea is if the light is aligned to the halfway vector between the microsurface normal, then you will have a reflection off of that normal towards the viewer. If the viewer is aligned to the halfway vector, not the light. And so by changing the, if there are more microsurface normals pointed away, then the light scatters off in various directions. But if more of them are aligned towards the viewer, then they will see a brighter reflection. So this is, shown here where as you increase the roughness of a surface, the intensity and the focus of the specular reflection increases or decreases and spreads out over the surface. In addition, there is a phenomenon that we need to model called shadowing and masking, which is where the microsurface and the specific component of the microsurface is obscured by higher parts of the microsurface. And so both of these phenomena we model with statistical models, which are based on physical observations, but however we do not physically model the actual geometry of the microsurface. In addition, there's another major phenomena that is called Fresnel reflectance. Augustin Jean Fresnel, I don't speak French, I'm sure I butchered that pronunciation, but he was a physicist who discovered some interesting properties of light. Mainly that the specular reflection has a color component to it. And so it's based on kind of these two broad categories of materials. And so we have dielectrics, which sounds complicated, but really it just means it does not conduct electricity. And so those are materials like wood, plastic, and skin. And then we have conductors, which are metals. They are conductive materials. And so the some of the interesting properties from Fresnel's work is that one, as the angle between the surface normal and the the viewer increases, the color of the specular reflection approaches 1, which is white in computer graphics. And so as you increase the angle with the specular reflection, all of them go to white. And this ties into this phenomena called Fresnel reflectance, which is where as you increase as you get closer and closer to parallel with the surface, the intensity and clarity of these reflections increases. And so when you're almost parallel to the surface, you get this mirror-like properties, whereas when you're closer to perpendicular to the surface, the reflection is almost impossible to see. In addition, conductive materials have a colored specular reflectance. This is why, for example, gold gets its signature golden sheen, is because a large amount of the light that is reflected from the surface is colored. But similar to all materials, as you approach 90 degrees to the surface, or 90 degrees to the surface normal, or parallel with the surface, the color of the reflection approaches white. In addition to this, rather than utilizing the actual Fresnel equations, which are quite complex, in real-time computer graphics, it is common to utilize the Schlick approximation, which is a quick linear interpolation-based approximation. And just looking at this graph, the dotted lines are the Schlick approximation, and the solid lines are the actual Fresnel values. And so for real-time applications, the approximation is good enough where the average user wouldn't even notice a difference between the two. But the computational complexity of the approximation is significantly lesser than actual Fresnel reflectance. So on top of all this, texturing is a key part of computer graphics because it provides a way for artists to give surfaces and materials more detail than they would be able to provide with geometry. In addition, it's used throughout the physically based pipeline to provide inputs to the shaders for calculating these physically based materials. And so within the physically based pipeline, there are kind of two main workflows. You have the metal roughness workflow and the specular glossiness. In practice, the metal roughness is the more popular one for no other reason than it just being the one that was largely adopted. And so you have the base color, roughness map, metallic map, and ambient inclusion, normal, and height. So the base color provides, as the name implies, the base color of the material. So this is the color, the kind of formal definition is the color without any sort of light influence, which is why it looks very, flat and washed out. The roughness map is used to feed these statistical models for the microfacets, and so that determines, how rough a certain point on the material is. Finally, the metallic map is used to determine whether a material at that point is a dielectric or conductive material. And so this allows you to mix dielectric and conductive materials onto a single, main material to give you, effects like rusted metal in this example. And then ambient inclusion is a lighting map that's used to kind of fake shadows. And normal maps, well, I'll talk about them soon. So texture mapping is the process of taking this 2D texture and wrapping it around an object. It's kind of like putting wrapping paper on a box. And so mathematically speaking, you use these projector functions, but which project the 2D plane onto the 3D mesh. However, in practice, it is more common to utilize a process called UV mapping, where artists explicitly map out the various points on the texture to the 3D mesh. This is mainly used because you don't have to compute the projection during runtime, and you also have a greater amount of control over the texture map to ensure there's the least amount of distortion. And so in practice, with every single vertex, there's a corresponding texture coordinate which maps to a point on the texture for the mesh. So as you can see here, this portion of the texture corresponds to the little faceplate of the knight. Now, normal mapping is a really important key concept in computer graphics. Rather than using textures to store color information about the surface, we store geometric information. And so the idea is that for each point on the texture, we are utilizing the RGB values of the textures to store a surface normal. And during shading, we're able to utilize these normal maps to fake extra geometric detail. And this is really just best shown, like many things in computer graphics, with the picture. And so as we can see here, without normal mapping, the surface is extremely flat. However, with normal mapping, there's a clear definition of the bricks and much more complex lighting. However, the amount of geometric detail in these two images is identical. So normal mapping allows us to increase the visual fidelity of the mesh without actually increasing the geometric complexity. Now in computer graphics, there are three main types of light sources. You have directional lights, which are modeled as infinitely far away light sources, and they emanate light in parallel light vectors. So you can think of this as like the sun. And so the sun, although it has a position, it doesn't, all of the light is coming from the same direction in this, I'm sure physics majors would cringe at that statement, but it works in computer graphics. Now, point lights, they have a physical position in 3D space, and they emanate light in all directions. And so this means that there is a attenuation of the light intensity as based on distance and angle. And so as you get further away from the light source, you see a inverse square decrease in the intensity based on the distance, which you can see here. Finally, we have spotlights, which are similar to point lights, but they have this cone of effectiveness that defines the light. And you can think of it as like a flashlight, so anything outside of this cone of effectiveness is unlit, and it gives you kind of a circular appearance. Now, the project was to, or at least the applied portion of the project, was to build a renderer with C++ and Vulkan. And so the idea was to build a robust renderer that was, composed of a API-specific portion and an API-agnostic portion, with the idea being that the API-agnostic portion would be what applications interact with, allowing for the backend to be swapped out without changing any of the rendering code. And so the idea is to utilize DirectX 12, otherwise known as D3D12, and Vulkan. However, the actual work for this project was spent on implementing the Vulkan backend and the API-agnostic portion of the renderer, with future work being spent on DirectX 12. And so the idea is just to build this robust infrastructure where, depending on the platform and hardware that you're on, you can swap out the backend without having to rewrite all of your rendering code. Now, Vulkan is a modern low-level graphics API that was introduced by the Kronos Group in 2016. So it provides an abstraction over graphics hardware, but it doesn't implement any of these rendering techniques that were discussed earlier. Now, compared to OpenGL, Vulkan is much lower level, with OpenGL being an older graphics library. And so it provides more it means that the developer has to manage more, but in exchange, the ability to really fine-tune the performance of the application and get performance benefits is significantly greater than OpenGL. Now, a big part of real-time computer graphics is performance. I mean, at a 60 FPS target, which is frames per second, that's 16 milliseconds per frame, super quick. And so, in this sense, RAM, reading from RAM is considered slow, which is something that many people wouldn't think of because RAM is typically thought of as fast. This is because over the years, the performance gap between memory and the processor has increased such that when you are trying to target 16 milliseconds, even just memory access patterns can be expensive. However, we utilize a architecture called the Entity Component System, which is really a special architecture designed for fully utilizing the CPU cache to reduce the amount of data needed from RAM. So the basic idea is, rather than having your typical object-oriented classes, you have entities, which are these stateless identifiers which point to various components. Now, the components are these pure state values that are stored with like components in a linear array. And rather than defining the state for components, you define these systems which are designed to operate over arrays of components. And so this allows for iteration over tightly packed component arrays that which means that you don't have to have a significant number of cache misses, which results in having to go to the RAM to load the data into system. And so this allows for extreme performance in real-time applications and is a common architecture used throughout the video game industry. Whew, okay, so I have a little demo showcasing the scene. A lot of information to cover, but I will show off the renderer. Okay, so this is the renderer. Now, this project is really more of a several-year project for me personally. The goal here was to get my IIS was to get a basic renderer up and running. But in the long term, I'm interested in expanding this to be a full-fledged video game engine. So currently we have a physically based renderer, which allows for the addition of arbitrary lights. So like right now, I can add in another light source, move it around, change the color. And so I've implemented some of the techniques discussed. They're physically based materials. My favorite of them all is normal mapping. If you look at just this, it really shows itself best on materials like tiles and bricks. You can see that it appears that these tiles are 3D when in fact they are not. We have a camera system, and so all of this is done in real time, as you can see, because I can move the camera around the scene, change perspective, and the scene is rendered as if I was physically standing there. And so a lot is happening in these 16 milliseconds. To give context, I can showcase. I'm going to be swapping screens a lot. We can showcase the application from the perspective of a profiler. So throughout the development process, profiling was an important process to try and see if there were any bottlenecks in the process. And so what we're looking at here is various components of the application running, and I can kind of step through them and what they mean. So a core part of this was to build a multi-threaded architecture, meaning that it can utilize multiple CPU cores for performance benefits. And so up top here we have the main thread, which is in charge of orchestrating it all. And so this portion is when the application starts and we're loading the scene. So we have asynchronous scene loading, which is happening here, meaning that the application is not frozen while it is loading the scene. Now, once the scene is loaded, you can see that things really start to get exciting. So what we have here is the multi-threaded draw call assembly. Now, there are about 2,000 objects in the scene, which means that we have to assemble 2,000 draw calls each scene. To speed this up, we split the work over multiple CPU cores and assemble these draw calls in parallel, and then we combine them all together and send them off to the graphics card. Now, because of this, most of the time is actually spent waiting for the graphics card to finish, because I am limiting the speed of the renderer to 60 frames per second as to not have it move too fast. Now, to peek into what's actually happening on the graphics card throughout the scene, we can look at a fantastic program called, finding something while talking is a little tricky, called RenderDoc. Okay, so RenderDoc is a graphics debugger that lets you see what's happening. And so here we can see all of the draw calls that were sent to the graphics card. And by stepping through them, we can see kind of a stop motion image of the scene being rendered. Now, all of this is happening in, milliseconds. But the real reason I wanted to showcase this is to show a special technique that is utilized in the graphics or in the renderer called depth buffering. So to ensure that objects are drawn in the correct order where something behind another object is not drawn in front, we utilize a special image called the depth buffer where we record the depth value, how far an object is from the camera into the scene. And as we are drawing new points in the scene, we just compare it to the value in the depth buffer and can determine whether or not it is, visible. And so if an object has a greater depth than the current value in the depth buffer, we just don't draw it. And if it has a lesser depth, then we draw it. And so this gives us kind of an eerie looking image where objects closer to the screen are white and objects further from the screen are black. And so as it passes through all of these draw calls, you finish with the final rendered assembled scene.